Hello. 1.2 is about limits, and the real idea in this section is to give you an idea of what a limit is, how to identify it from a graph, and how to evaluate a limit using direct substitution. In future sections, we will talk about other strategies when what we learn in this video doesn't work, but the real goal here is that we can understand what a limit is and how to find it. So the first thing that I think of when I think of the word limit is I think of the speed limit. And when you're driving on the road, typically the speed limit tells you the maximum speed that you are allowed to go. But I think that many of us know that our goal is to maintain a speed right around that limit. A little bit above or a little bit below keeps us in a safe zone in whatever neighborhood, freeway, etc., wherever we happen to be driving. So our goal is to sort of hover around that limit, that value, whether it is a little above or a little bit below. In math, a limit describes the y value that a function approaches as it goes towards a particular x value. This is really similar to just evaluating a function. If we talk about a function that is continuous, that is exactly what we are going to do, but it's really looking at what's happening to the y value or to the function itself as I get really close to a particular x value. We're going to talk about notation a little bit here and some one-sided limits and what happens if a limit doesn't exist, and then we're going to start jumping into looking at a graph and identifying limits from a graph. So, notation. If I was to read this out loud, I would say the limit as x approaches c of f of x is equal to L. And here we are assuming, or we are stating that L is a number. It is a particular value. And that's how you would read that. The limit as x approaches c of f of x is equal to L. There's also something called one-sided limits, where instead of just approaching from both sides and thinking about what's happening around that limit, you actually might just consider what's happening either from the left or from the right. So let's look at that notation. So the notation for one-sided limits, where we're just considering what's happening either to the left or to the right of our function at a particular c value, looks a lot like the regular notation, except you're going to see superscripts or little symbols above your c. So if you see a minus sign above your c, it sort of looks like c to the power of a negative sign. But that means that we are looking at the left-sided limit. So we're taking our finger and we're dragging our finger along the left side of the function and seeing what happens as we get close to c. Versus if there's a plus sign in that superscript, that would be a right-sided limit. So we're actually starting on the right of the function and moving towards the function, meaning we're moving to the left to get to the function and seeing what happens. And I'll show you what this looks like on the graph. But right here, I just want you to know that we can look at just one side of a limit instead of looking at both. And when we do that, I want you to recognize this notation. There are a lot of different types of functions out there, and not all functions have limits at every single value. So if you think about what we have talked about previously, we've talked about functions that have a hole or that have maybe a jump discontinuity, and in certain cases, having some sort of funky thing happening in the graph actually could mean that the function doesn't have a limit at that particular value. And when that happens, we say that the limit does not exist. So when the limit does not exist, we use DNE to say the limit does not exist. DNE. So I'm going to just briefly mention the 3 reasons that this can happen when you're looking at a graph. So one thing that I briefly mentioned is that there could be a jump in the graph, meaning when I'm coming from the left, it's approaching some number, but then it jumps up and starts doing something totally different. So this is one reason that the limit would not exist. It wouldn't exist at this place where we have a jump in the graph. Another reason that the limit might not exist, or that the limit wouldn't exist, is if our graph is approaching a vertical asymptote. So, meaning that I have a graph that from one side is getting closer and from the other side could be getting closer as well, but it's never actually getting really, really close because there's this vertical asymptote that our graph can never touch. So that would be another circumstance in which our function, or in which our limit, would not exist at that particular value where we have the vertical asymptote. So if this was at x equals 1, we could say that the limit does not exist when x equals 1 because there's a vertical asymptote. And the last reason that the limit may not exist is if our graph has an oscillation happening, meaning that if you actually looked at the graph of the function, when you're getting really, really close to something, you can't tell what's happening because it's moving so fast, or it's going back and forth between a handful of things. A great example of this is if you look at the graph of sine of 1 over x, if you just typed it into Desmos, and then you tried to get really, really close to 0, it's hard to tell what's happening. It's almost like the graph is jumping around. So that would be an oscillation. And all three of these reasons, a jump, a vertical asymptote, and an oscillation, are all reasons that a limit would not exist at a particular x value. So now that we've talked about the notation, we've talked about reasons that a limit might not exist, and we've talked about what one-sided limits are, let's actually look at a graph and dive into some examples of identifying limits from a graph. So here we have graphed y equals f of x, and this is a function that has a lot of different things going on. I see some holes in the graph, I see a vertical asymptote right here, I see some sort of jump happening here. So lots of different things going out that could impact our limits. So let's work through each of these problems together. This first box up top says the limit as x approaches -4. So what I'm going to do is I'm going to look at my graph. I'm going to look at what's happening as I get close to -4, both from the left and from the right. And as I get close to -4, both from the left and from the right, I'm getting really, really close to this number right here. And remember, the limit is the y value. What is the y value at that point? That y value is 1. So the limit as x approaches -4 of f of x is 1, because as I get close from the left and as I get close from the right, I'm getting close to the y value, negative or positive 1. The next thing we're going to look at is the limit as x approaches -1 of f of x. So here is where x is equal to -1. Looking at the function now, as I get really close from the left and as I get really close from the right, I'm getting really close to one y value. And both from the left and from the right, that y value is the same number. Now, at the moment that x is -1, there's a hole in this function. But the limit's not asking you about what's happening exactly at -1. It's asking you about what's happening right before and right after. And right before and right after, we have what I would call an agreement on the left and the right. They are both getting really, really close to the y value of 4. So we would say that the limit as x approaches -1 of f of x is 4, because both from the left and from the right, we're getting really close to the y value of 4. Now the limit as x approaches 2, so I'm going to get close to 2 from the left, I'm going to get close to 2 from the right. Both of those are in agreement. They're both getting really, really close to the y value of 1. So a function doesn't have to exist at a particular value to have a limit at that value, as long as we're getting really, really close to that same number from the left side and the right side. What we're going to look at to fill in this second row of the table are actually not limits. There is no limit as x approaches a number here. We're just finding the value of the function. So the first question is asking us to find f of -4. So when x is -4, what's happening? It looks like the function is at 1. When x is -1, we're looking for the closed circle. Since we're not talking about the limit, the value of the function when x is -1 is 1. F of 2, the value of the function when x is equal to 2. So I want you to notice that this is an open circle and there's no ordered pair somewhere else on the line. So this is different than what's happening when x is equal to -1. F of 2 does not exist because there is no filled in circle anywhere along the line x equals 2. In the next row, the limit as x approaches 3. So looking at my graph, as x approaches 3, which is right here, we have a vertical asymptote. And that was one of the reasons that we said that a limit would not exist. So the answer here is that this limit does not exist. The limit as x approaches 5. So if you notice here, is what's happening when x is equal to 5. We have an open circle and a closed circle. That is a jump in the graph, which means that limit will also not exist. However, the function does exist there. The function, the value of function when x is equal to 5 is 2. The value of the function when x is equal to 3, well, it doesn't ever actually get there, right? Because there is a vertical asymptote. So the value of the function there does not exist. And then we're going to look at left and right-sided limits. So this one down here says the limit as x approaches 5 from the right. So I'm going to go far, far to the right, and I'm going to get closer and closer and closer to the function. As I get closer and closer to x equals 5, I'm getting closer and closer to this number, which is 2. So even though the two-sided limit doesn't exist when x is equal to 5, when I approach it just from one side, it will exist. Similarly, if I approach x equals 5 from the left, I'm getting closer and closer and closer to this y value, which is -1. So just because the limit does not exist doesn't mean that one-sided limits don't exist. So when you're analyzing a graph, make sure you're remembering the 3 reasons that a limit might not exist. If we have a vertical asymptote, if we have a jump, or if we have an oscillation. And remember that when you're being asked to find the value of the function, you're looking for the point. And when you're being asked for the limit, you're looking for what's happening right before and right after. And then one-sided limits, you're looking at just one of those things, either what's happening right before on the left or what's happening right after on the right. To help you understand a little bit more what we're talking about in an equation sense, what I want you to do is, if you have a graphing calculator to find that, otherwise open Desmos, and I actually want you to graph the function part of what you see here. So you're going to graph 3x squared minus 4 and x plus 1. And then what I want you to do is to use the cursor tool to drag and to figure out what happens for each of these at these different x values. So 2.99, 2.999, etc. So what you'll see is if we're looking for the limit as x approaches 3, I'm looking at some numbers that are below but very, very close to 3, and some numbers that are above but very, very close to 3. So I encourage you to pause the video, to find a piece of technology that can help you, and to fill in that table with the numbers that you see when you are getting close to those values. So here is what I'm seeing. When x is 2.99, 5.7194, and then 5.7469, 5.7497. That's what's happening right below. So it looks like it's getting really, really close to 5.75 when I'm coming from the left. Once I go a little past 3, 5.753, 5.78, it looks like I'm still sort of hovering around that number. So for right now, we can say that this limit looks like it is approximately 5.75 if we look both from above and from below. Using the same logic, I encourage you to pause the video and work through 2 and 3 and see if you can come up with what number we're getting close to by filling in this table. Then unpause the video and see how you did. So on number 2, all of the numbers that I plugged in to the left gave me exactly 1. And even when I went to the right, I was getting exactly 1, which makes me believe that this limit is approximately 1. And I'm putting approximately because we haven't really done any math to verify this other than just analyzing what we see. So we're still making a guess here. And then number 3, it seems to be hovering around 1.25 both above and below. So the idea here is we looked at a graph. Now we're looking at what's actually happening when we plug in x values, when we plug in numbers really close to the number that we're taking the limit of. And that leads us to how we could possibly solve or evaluate a limit when we don't have a graph, but we actually have the function itself. And when we have a function that is continuous, meaning we don't have those holes or vertical asymptotes or big issues happening, at least not at the value that we care about, which we're going to call x equals c. If a function is continuous, then the value of the limit is going to be exactly the same as the value of the function. So let's look back at one of our graphs for just a minute. Right here, that limit that we took gave us that the limit as x approaches -4 was equal to 1. Well, that is also the value of the function, and that makes sense because I'm just going right through with no big issues such as a hole or a discontinuity. So when we have a continuous function, or at least a function that's continuous at a particular value, and we're going to focus on that idea of continuity in another video, you are allowed to simply directly substitute in the number that you're taking the limit for. So, for example, here on number 4, the limit as x approaches 3 of this quadratic is just going to be exactly the same as whatever you would get if you plugged in 3. So 3 times 3 squared minus 5, 3 times 3 squared, well, that's 3 times 9, 27, minus 5 is going to give you 22. The limit as x approaches 1 of this function, and this function I want you to think about for a minute, this function only has issues with discontinuity when the denominator is equal to 3, or when the denominator equals 0, meaning when x equals 3. So at 1, we're okay, which means we can use direct substitution here. So 1 squared minus 3 times 1 over 1 minus 3. I'm substituting this x value in for all of the x's in the function. This would give me -2 over -2, which is just 1. For number 6, the limit as x approaches pi, well, cosine is continuous everywhere, right? It oscillates up and down between -1 and +1, but the function itself is continuous everywhere. So this limit is equivalent to what I get if I just plug in pi for my x value, which would give us cosine of pi over 3, which is 1/2. I encourage you to pause the video and see if you can work through 7, 8, and 9, and then unpause the video and see how you did. So hopefully you have had some time to look through the video and to work on 8, 7, 8, and 9. We're going to work through them together now. The limit as x approaches 0 of 3. So what I want you to notice is there is no x value here. The limit of 3, right, this is just a graph, a horizontal line. That is y equals 3. There is no x changing it. So the limit as x approaches 0, well, it doesn't matter at all what x is doing. There's no x to directly substitute in, so that answer is just going to be 3. The limit as x approaches 0 of 3 is 3. The limit as x approaches anything of 3 is going to be 3. The limit as x approaches pi over 6 of tangent is going to be tangent of pi over 6. And just as a reminder, that would be the same thing as saying sine of pi over 6 divided by cosine of pi over 6. And we can use the unit circle to help us here. Sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. And I'm actually going to rewrite this using what I like to refer to as old school division, because it helps you remember that to do this, you can just flip and multiply. So this is the same as saying 1/2 times 2 over root 3. So those 1/2s are going to divide out. That's going to give us 1 over root 3. And remember, you do not need to rationalize your denominator. You can leave it just like that. And then the last one, this function is continuous, or we don't have any issues. If I plug in 1, I don't get something weird. I don't get something that's not allowed. So this limit is going to be equal to 1/3 plus 4. Well, I can find a common denominator here, 3 over 3. So that's going to give me 1/3 plus 12/3. That's going to give me 13/3. And that is the end of this section. So let's recap what we talked about. We talked about notation and how to read limits. The limit as x approaches c of f of x is equal to a number L. If that limit exists, we talked about the 3 reasons that a limit may not exist. jump, vertical asymptote, oscillation, and we talked about the notation and how to look at both left and right-sided limits. We then spent some time looking at a graph and analyzing the limits from a graph, as well as looking at a table or completing a table to look at a limit from a function. We wrapped up by evaluating limits using direct substitution, which we are allowed to do as long as a function is continuous at the specific value that we are looking at. So if you have any questions, make sure to write them down or post them on the video below, and I look forward to supporting you more on this. Thanks for listening.